Here are solutions to homework set number 8 for ECE 320. The first problem is find the voltages and currents for a DTL logic gate. Now the first trick is to figure out which diodes are on, which ones are off. I've got 5 volts trying to push current through here, so probably this diode is on, this one's on. That'll probably saturate this one. So this is saturated. This will be 0.2 volts. 0.2 volts isn't enough to turn on this diode, so this one turns off, which turns this off, and that's roughly 5 volts by voltage division. So the actual current is going to be 5 minus 2 diodes, 5 minus 1.4 over 50K. That gives you the current for I2. This current is 4.8 volts over 1K, 4.8 milliamps. This voltage by voltage division is going to be 50 over 51, that percentage, 5 volts. And the current is 5 volts over 51K. So when you do all that, these are the voltages and the currents. Basically, this is an OR gate. If either input is 5 volts, the output is 5 volts. A little bit less due to loading. Problem 2. Check this in Circuit Lab, and when you throw that in Circuit Lab, you get the same answer. Again, the numbers aren't quite as nice. It's not exactly 1.4 volts across the diode, or 0.7 volts across the diode. That's kind of a ballpark guess. So these numbers will be close, a little bit different, but close. And when a transistor is saturated at V3, we're assuming 0.2 volts when saturated. Again, that's kind of a ballpark. Close to 0, but not quite. Turns out close to 0, but not quite. It's actually 101 millivolts. Problem 3. Determine the voltages and currents for this NAND gate. So again, this is a min function. The current can go left or right. Going right is 1.4 volts, 2 diodes, 0 volts or 0.1. So this is the one that's going to be on, the lowest voltage. This one's off, and this one's off, making this 0.7 volts. If there's no current right, this is off, and there's no place for the current to go, so that's 5 volts. I can now have this current go right, so these turn on, and I'm at 1.4 volts. And probably this transistor saturated, which put the output at 0.2 volts. So when you do that and calculate the currents, again I have 0.7 volts, 5 minus 0.7 over 50K gives you 86 microamps, nothing. 5 minus 1.4 over 50K gives you 72 microamps. That allows 7.2 milliamps to flow. I'm only trying to push 4.8, so this saturates. If I check in Circuit Lab, build the circuit, take the voltages, again, I get very similar answers. What I calculated is a little bit different than what I simulate. If I build it, it'll be a little bit different, but close. This diode is turned on, about 0.7 volts. Q2 is off, 5 volts. V3, I've got 2 diodes, about 1.4 volts, and V4 saturated, about 0.2 volts. Problem 5 is to analyze a TTL circuit. Now when the input is 0, the current goes left, so this turns off. When it's off, it'll be 50 over 51 times 5 volts, about 4.9 volts. Ideally 5 volts, minus a little bit due to loading. When this is 5 volts, then instead the current goes right. That'll saturate this transistor, making the output 0.2 volts. So this is a TTL inverter. 0 volts in gives you 5 volts out. 5 volts in gives you 0 volts out. And if you calculate the currents, these are the currents that you're going to get. The oddball of this one is because of the doping on the transistor. This is an NPN transistor. If this doping is 1, this is 200. So the current gain is 200. For every hole, I have 200 electrons. If the doping over here is 2, then when I have current going the opposite direction, I treat this as the emitter. For every hole, I have 2 electrons. So beta changes depending upon how you use the transistor. Used correctly, beta is 200. Used incorrectly, beta is 2. And I do that because this 72 microamps is amplified by beta. I want that to be 0. It won't be 0 because they need some doping to make it a transistor, but keep it small so don't draw too much current. If I simulate this in Circuit Lab, if I double click on this, saying this way, the gain is 200. I get very similar voltages and currents. Going the other way around, I'll flip that transistor, make the gain 2. And now when I calculate it, my calculations again pretty much match what I get in Circuit Lab. The numbers we get are close, again saturated with Sp23, close to 0 but not quite. Problem 7 looks at using DTL logic to build a temperature alarm. So here what I have is a 555 timer outputting a square wave. When this is 5 volts, the alarm turns on. When this goes to 0 volts, then what happens is when this is 0 volts, this diode turns on, this is 0.7, these turn off. So this is my on-off control. 0 volts is off, 5 volts is on. To control that, I can use a comparator. When the temperature gets too hot, I want this to output 5 volts, saying the alarm, turn on the temperature alarm. So again, the kind of two cases are when the input is 5 volts, this works. When this is 0 volts, there's the alarm is off. In Circuit Lab, I can test that. Again, this is the part that I care about. When both inputs are 0, I get the transistors off. When both inputs are 5 volts, the transistor's turned on, or current flows through the speaker. That's supposed to be the speaker. It's actually an 8 ohm speaker, spelled, with a 20 ohm resistor added to limit the current. And I want to limit the current to about 200 milliamps because that's all a 3904 can take. In terms of hardware, if I build it, here's the hardware circuit. Here's my 555 timer outputting a square wave. Going to my transistor, here's the DTL logic and my comparator. To test it, what I would do is take the comparator, take this point right here, tie it to ground, and the speaker should turn off. If that works, then take that point, tie it to 5 volts. Speaker should turn on. If that works, then take this, tie it to the comparator. As the comparator goes through 1.8 volts, the speaker turns on and off. Why is it not working? You can try that again. Here's the wiper. I get anything between 5 volts and 0 volts when I adjust the wiper. If I set it up to turn on about at 2 volts, nice round number, I can then go over and look at the voltage across the thermistor. In there. Oh, baby dog. As I heat up the thermistor, the voltage should drop. That's what's being displayed, the voltage across the thermistor. When it drops below 2 volts, the speaker should turn on. So trying that. So 2 volts, it turned on. Let it cool down. As it cools down, the voltage goes up. 2 volts, it turns off. So afterwards, what you can see is you can take some measurements and see where the speaker turns on, where it turns off. It depends upon that pot. If I set it to 2 volts, that's where it turns on and off. Adjust it to 1.8 volts, that's where it turns on and off. So that's homework set number 8 for ECE 320.